the quantum effect. I want to talk about something called Coulomb blockade. So what is that? So I have something called quantum dot. Now this is showing a capacitor or the band diagram. You can think of that. So this is the quantum dot. I don't know how you do that, right? You can try a way to create something. Of course, you can think of this easily. Just think about when we talk about FinFET. We make it very narrow in one dimension, another very narrow in another dimension. So narrow wire, I should say narrow wire. And then in the third dimension, you have the gates to turn it on and off. Then you form a one-dimensional quantum dot, which means that the electron is surrounded by the barrier in all directions. Okay? So this is something like this. Is this okay? Do you understand what I'm talking about? Of course, now I'm only looking in one dimension, so you confine the electron here. So I have an electron. Can have one electron, two electrons, many electrons. It's just like I confine you in a room. I confine you in a room, the wall are the barrier for you. Why you cannot just leave the room? Because the wall has higher energy than your current energy, right? If you have high energy, I don't know how much energy you need to tunnel or go over the barrier of the wall, right? Then you won't be confined, right? Then it's not a then you can leave the dot. Now the idea is this. When you have a dot, it has a capacitor. Okay? So basically, this is like an insulator. So isn't that I will get a capacitor here, left and right, right? That connect me to the ground. Just think about now another quantum dot you can think of is this. What if you have a wire physically and then you have an insulator, then you form two capacitors, you make them very close, very close, very close. Eventually, you confine it in a very small region. And because it's a wire, you cannot go in the perpendicular direction because you need to leave the wire, right? So it has a capacitor, I call it C. It has a capacitor to the ground. So if I add a charge add Q to the dots, I add charge to it. Now let's say there's nothing, right? Or whatever, there's no excess electron or excess charge. I add some charge to it. Then it's going to gain energy, right? We're adding energy to it. And the energy E is equal to 1 over 2 Q squared over C. This is just what you have as a capacitor. In a capacitor, if you put in charge of Q, then the energy is half Q squared over C. Okay, so this one I will ask you to learn it yourself if you have not learned that. Okay. Now, so if I have n electrons, right, then what is the energy? I call it En, right? Because we're dealing with electron, charge is electron or hole, En is equal to half, then the total energy, which is total charge times N divided by C, right? Each electron have E amount elementary charge. I have N of them, 3, 4, 5, times that is the total charge. Q squared divided by C. So this one gives me this, E squared divided by 2C times N squared. Make sense? Now, so this one only depends on elementary charge and the capacitor, so I'm going to call it EC. It's not conduction band H now, right? We're talking, no, band diagram, EC, charging energy. Later you will see that for one electron, right? So if I have N plus 1 electron, Then what is the total energy in this system? If I n plus 1. Very good. ECn plus 1 square. ECn plus 1 square. And now is the question. How much energy? Energy needed to increase electron from n to n plus 1. So you already have n electron there. Now I want to tunnel 1 electron into it. How much energy do I need in order to add 1 electron to it? Of course, then you find the difference from the n and the beginning, right? So it must be E n plus 1 minus En, which is equal to EC n squared minus n plus 1 squared minus n squared, right? Because ECn plus 1 squared is the amount of energy you have after you put in 1 electron. And ECn squared, it was the amount of energy you have before you put in the electron. Make sense? Any questions? Which is equal to EC times 2n plus 1, right? Because the n squared got cancelled. This is important. Any questions? Are you okay with this math? Because later we are going to rely on this concept for the single electron transistor. Okay, so that's why we say this is the charging energy. Right? It's the energy. If I want to put in 1 electron, it's not that easy. I need to have enough energy to put in 1 electron, or that electron need to be energetic enough so that when it goes in, you will make the system energy to increase by 2n plus 1 EC. Right? So if we look, just quickly draw a table, right? The energy needed, not here. What should I call it? I try to add electron. The first electron, second electron, third electron from 0, right? And then when I add the first electron, I get 1 electron, right? 2 electron. Maybe I just follow my cheat sheet. I will start from 0. Right? I start with no electron. And because we're doing n plus 1, so it may confuse you if I change it now. I start with n equals 0, right? So what's the energy I need in order to add 1 more electron? From 0 to 1, how much do I need to add? EC. Thank you. Right? Because n equal to 0. I start from 0, right? So I add EC. But I add 1 more electron. How much do I need to add? Not yet. So free EC. Because now n equal to 1. From 1 to 2. Right? And I want to add 1 more. How much more do I need? 5 EC.
Doesn't this scale?
You can say that. No, how to say? It you double, right? 2n. But yeah, that's just a prefactor. It's not equally spacing, right? Because of 2. Yeah? So it's not harmonic oscillator, but something like that. But you're right. Like harmonic oscillator, we have a discrete level of energy now. Think about that. Right? Add 1 more electron, the whole system increased by 2n plus 1. It's discrete and becomes larger and larger. And I've not talked about Coulomb blockade, but you already maybe see that already. There can be situations in which that you don't have electron in this quantum dot. I can tunnel electron into it easily because I only need energy of EC. But if there was already 1 electron, Now, let's say I only have 2 EC of energy, I cannot get in. Because this time I require me to have 3 EC in order to get in. Make sense? Yeah? So the blockade comes from here. If there's 1 electron, I cannot go in. No electron inside, I can go in. Now this is very useful. It means that we might be able to control electron one by one into the device if we do it well. Now, isn't that cool, right? Electron is not like a ball that you can carry basketball one by one into the room. How can you control it electrostatically so that I just have 1 electron inside? And that has a lot of implication. And the reason I bring this up is because in silicon qubit, you use single electron transistor to sense whether you have 1 electron or not. And that you have 1 electron or not actually depends on the spin of the electron in your qubit. So you have taken E274, right, last year, right? You may know that. That is how we sense the silicon qubit. We use spin to charge conversion, and then use single electron to sense whether there is such a charge there, right? So we will start talking about this single electron box. So what is this? It's just like quantum dot. This is a quantum dot, an island. As long as I'm isolated, when I say it's isolated, how can you get isolated? Because you have barrier, you cannot get out, right? So it is a quantum dot. I don't care how you isolate it, right? But usually we just isolate with insulator. As a result, you have capacitor. In this case, it is very simple, only 2 terminals. You have a source, you have a gate, and we design it so that you can have tunneling from the source to the island. Okay, we allow tunneling, maybe thin enough, right? But there is no communication, no transport between the island and the gate. You make it far enough, right? So that is how you need to design it. If you cannot do that, then that is secondary effect you need to take into account in your design, right? That is the work for engineer. So this, we have some math, but the most important is to understand the setup. Now, because of this, the source is grounded. The gates, of course, it must come from the ground and then apply a gate voltage to it, right? So I apply different gate voltage, what will happen? Then you are going to induce positive charge here, negative charge here, and then positive charge here, negative charge here. But remember, we allow tunneling, okay? It can go in and go out, right? So this is not an isolated system. This one can have the number of electron changes depending on the gate voltage. And we are going to show you that we are able to control the gate use the gate voltage to control individual electron, the electron number inside the island can be so precise, right? You may feel that, is it possible? Do I need to control up to 0.0001 microvolt in order to get 1 electron? No, because when you are a quantum dot, you will be able to have a pretty large range. So we will go through the math. First, we look at the energy of the system. The energy of the system is equals to half Q1 squared I hope that I can finish. Q1 squared divided by C plus Q2 squared divided by CG. That is just the capacitive energy we discussed earlier. Q squared over C half, right? That is what we're doing. We have Q1 across C. This is C. This is CG. Make sense? That's it. But we also need to consider the fact that in order to put a Q2 here, we also need to have work done through the gate voltage. So it's Q2 times Vg. Okay, we don't want to go to detail, but That is the total energy to form this system from nothing. Okay? Now, that's okay. Right? So this is given. That is the total energy. Then what I'm going to do is that I actually copy this from this book, right? I also put in the reference. And you should be able to download it or view it from our library. Okay? You can go back to do the derivation if you cannot do it, but I will just show you some concept. I do not derive it. Of course, then we have CV1 equals to Q1. So what is V1? V1 is talking about the potential drop here. V2 is talking about the potential drop here. Okay? So naturally, CV1, CV equal to Q, right? And then, sorry, I might put in the wrong direction. But depends on how I define the arrow. So I'm not going to correct it. CV2 equals to Q2. Right? And then using KVL, of course, V1 plus V2 must equals to VG. Right? Because this is graph. So here comes to here must be equal to VG. Right? And what is, and then of course, then you can also further say because we have V1, V2 already. V1 is Q1 divided by C plus Q2 divided by CG. Right. Now, what important here is the rest are just math, but I want to define an important quantity. Define what is the total number of electrons in the quantum dot? It's E times M. The charge times N must be equal to Q1 minus Q2. Right? Because this is positive Q2, positive Q1, negative Q2. This gives me the net charge in the quantum dot. And that is the total number of electrons. Right? So this is the definition you need to understand that what is the meaning of capital N. Right? So N is the number of electrons in the well. Let me call it well or dot, whatever. Okay? We define one more quantity. This is just a definition. Q equals to negative CG VG. Now, you see that it is not here. You don't see the Q here. You don't see it. But it just defined as the gate voltage times the capacitance, the gate capacitance. Just a definition. Now, you might see this already if you took EE274 when we do the superconducting qubit drive, right? You can relate to this later. But just a definition, so do not ask what is Q. Q is just a quantity, Vg times this capacitor. But you can understand as the charge induced by Vg, right? So if I don't have Vg, Q equals 0, I don't induce anything. Okay? And that's it. Right? Then you solve it, which you can refer to the textbook. The final thing is that we need this equation. This Q, no subscript. It's just defined as negative CG times VG, a new definition. We solve it, then we get this one. The system, the energy of the whole system equal to EC. We have EC again. I will talk about this later. N minus Q over E. E is just electronic charge minus Q squared over 2CG. Now, you will get this. You've just solved it. You don't need to do that. But I want to tell you that what is EC? Do you remember what is EC? What does it mean from the last line? Very good. It is just the charging energy of one electron, right? That's what you say, Q squared over E squared over 2C, right? In this case, because now we separate the capacitor, so it's going to be equal to E squared Instead of 2C, it's just C plus CG. Right? Because now we call this as C and this as CG. Earlier, we call both of them together as C. So it's the same, right? This is the first definition. I thought I still have one more. But anyway, so that's good. So memorize this equation. Not memorize. I mean, this is the equation, right? So what does it say? It said the energy of this system equals to the charging energy times N minus Q divided by E. Now, this is important. In the previous case, it is just Q number of electrons, just N, EC times N squared. But now it's N minus Q divided by E squared. And what is Q again? Q is the charge induced by the gate. So if I can change the gate, I will change N. And then I'm going to change the behavior. And let me show you how. So from the last part, right, we have, let me copy again, E equals to EC N minus Q divided by E squared. Let me copy also the second term. This is just from the last slide. Minus another term, Q squared divided by 2CG. Okay? Now, since this Q squared divided by 2CG does not depend on N, and now we're interested in N, we will just ignore this term. Okay, we will just ignore this term because it has nothing to do with N. Right? And then we change this to EL divided by EC equals to N minus Q over E squared. Then I plot on the right Q over E divided by EC, which is just the EEL divided by EC. So we start with N equal to 0. I plug in. This is a quadratic equation, right? I mean quadratic behavior, right? For N equal to 0, right? I'm not going to draw it. You get this curve, right? Correct? When N equal to 0, you just think that Y equal to X squared. This is Y equal to X squared. Do you agree? Quadratic when N equal to 0. Now, what if I say I already have N with what? How many electrons in the dot? So there's no electron in the dot, then the energy depends on E, Q over E in this way. What if I say there's already one electron in the dot? Then it will follow this because now you have 1 minus X squared. This is 1 minus X squared. If you actually let one electron, maybe positive charge, then you have N equal to minus 1. Then you have this relationship, right? Correct? Okay. And now the question is this. If for a given Q over E, but what is Q again? Very good. It's negative CGVG divided by E. So basically, it's saying that for a given VG, right? It means that, okay, you put a VG there, 0.5 volt, 20 millivolt for a given VG. For a given VG, then it means we're talking about this vertical line. For example, let's say I have this. This is the given Q over E, or in other words, a given VG. Then I'm in this location, right? Where would this one end up at? It will always always what? Retain or always go to the lowest energy. How do you go to the? Right? Correct? I did not say how many N is there. I just say, now I put so much Q over E here. Then I can have N equal -1. I can have N equal 0 or N equal -2. This is N equal -2, N equal to 0, N equal to -1, right? So here, for example, there will be N equal to -1. So it's just saying that if you have a certain gate voltage, this graph will tell you how many electrons will be in the box. Okay? So then it means what? You can adjust the N by tuning Vg. And the range is pretty large. Right? For example, if Q over E is less than 1/2, less than -1/2. Do you see that? If I put a Q over E between -1/2 and 1/2, which curve has the lowest energy? N equal to 0, right? Because N equal to 1, N equal to -1 or 3, 4, they all have higher energy. They will always get you N equal to 0. And again, because Q equal to -Cg divided by Vg, then it is saying that -1/2 less than -Cg times Vg not divided, right? Will give you let me write one more row. This is equal to -E/2Cg equal to -Vg, not equal to, less than E/2Vg, if Cg. Can you see it? Maybe difficult, right? But anyway, my goal is to say what? If your Vg is between this range, you will always get N equal to 0. But how large is this range? I'm talking about E over Cg, right? Can you see this? E over Cg. How can I make this very large? If this is large, then cool. I can adjust from -1 volt to 1 volt. I still have only 0 electron in the well. How can I make it large? Make Cg very small. And that's why you need quantum dot, right? Because quantum dot is small, so you have a small capacitor, right? So one, you need large node. You need small Cg. But another important thing is you want to have a low temperature, because all we are talking about here is about the electron can only do tunneling. It cannot go over the barrier. A barrier, this energy separation, which we show here, EC, 3 EC, 5 EC, they are still pretty small, right? So that's why when people want to see this Coulomb blockade in the past, they need to cool down to 1 Kelvin, 4 Kelvin. Until later, maybe they have very good technology, go to nanotechnology, they have quantum dot, all this new fabrication technology, they will be able to see at a higher temperature. But both of these are necessary, and that's why this is related to cryogenic. Okay? Right? Again, why is that? When we talk about this Coulomb blockade, it's saying that if I only have 2 EC, I cannot add second electron. But if I have thermal energy, I have more than 2 EC, then I can just jump in EC. You won't see the quantum effect. Okay, so that is one thing. Yeah. Negative, it just means that you have one less electron, so you have positive charge. Yeah. Then we introduce another concept called periodicity. Let me just write down what it means, then you will understand. So if the induced charge which is Q, right? Q is what? Due to the gates, right? Negative Cg times Vg. Induced charge and state. I mean, if the induced charge is Q, sorry, is Q. Right? If it is Q and the state is N, what does it mean? For example, the induced charge may be at this point. Okay, this is the induced charge Q, of course normalized by E. And the state is N equal to -1, right? Because this has the lowest energy. Okay? Then it has the same energy as Q plus E times M with N plus M electron. So what does it mean? It's just saying that now this is the state, that what if I shift it to here? This one has the same energy as this guy, right? But in here, this becomes N plus M equal to -1 plus 2. Okay? And then the charge becomes Q plus EM, which is equal to, I don't know what it is, let's say -3 divided by 4 plus -3 divided by 4E, right? Plus E times plus 2. Right? Here. Which is about 1 and 3 divided by 4. Right? That's trying to say this periodicity. So if you you have this type of degeneracy for the same energy, right? If you put this gate voltage, right? Because induced charge related to the gate voltage you put, and you already have this amount of electron. Now I increase this voltage by this amount, E plus by, so that you have E times M, more charge, induced charge. That is the same as if you will also have N plus M electron in the system before. Not very important, but look at this periodicity, right? And if you can understand, I'm not going to test this. If you can understand this, it help you really understand this graph better. Okay? Any questions? Good, so we are done with the second fundamental system. Now we can look at the single electron transistor. It will be easier to understand now. Now it has three terminals. Each of these terminals are coupled to this quantum dot through a capacitor, Cl, Cr, and Cg. It's a transistor, so of course you have a gate, you have source and drain. Now source and drain, I put the bias here, VL and VR. Right? It don't operate usually like what we usually want to make it symmetric, so we have the voltage on both sides. I will show you later. Right? Of course, you also can put this as ground, but then the math is a little bit more complicated. Okay? So, how can I, we'll do that later. So one is the total energy of the system. It is E, we are not going to derive it. We just take it for granted, but you will see that you will agree because it's same as what we derived earlier. Okay? But here, what is EC? EC before was what? The charging energy of single electron, which is E squared divided by 2C, right? But here, what is 2C? Cl plus Cr CL plus CR plus CG. This is the EC, right? And then how about what is Q now? Q again is the charging, charge induced by the gate, but not just gate now because we have free electrodes. Here we only have one electrode, not electrode, I mean voltage source, right? Here we have free. So it turns out this is a convenience way, right? So it is equal to CR times VR plus CL times VL plus CG times VG. Right? We don't care too much about this. I don't need to go into too much detail, but I just want you to see that how it evolved from simple quantum dot to the previous one with one voltage source, now have we three voltage source. I just want you to feel comfortable of seeing this equation now. I could have just started with this, right? As you say, just accept it, but I hope that at least you have some idea what is the meaning of this stuff, right? Right. It turned out that actually I forgot either a copy wrong from the textbook or it turned out it's just a definition, right? So later in the equation you just fit the sign. So I don't care too much unless you want to really do the calculation. Yeah. But you are right, need to be careful. So here we say that, right, we assume we have n electron in the box or the dot. How can I change the number of electrons? Same as last time, I allow tunneling here. Right? I allow you to tunnel to the left and right, but not to the gate. I make it really, separation really large, right? So there are four possible reactions. We call it reaction. You can have from n electrons becomes n plus 1. So what are the process? From the left and to the right. These two process. From the left, not to the right. I say it wrong, right? How do I get one more? From the right. Thank you. Right. You can have electron come here or electron come here. Right? I also can have from n electron becomes n minus 1 electron, right? So what are the possibilities? To the left, to the right. Okay? So very simple, right? Now, because of time, I won't start the next one. Maybe we just stop here. This is to the left, right? This is from the right. So let's stop here. The reason I want to cover this first is once we finish this, then this is a part of your assignment 4 also. Okay? So let's stop here.